All right, good morning, everyone. So in today's lecture, we will start out with body waves and how we name different phases that travel through the Earth. And then we will talk about some ray paths through the Earth. And then we will talk about the composition of the Earth. And then we will go into attenuation and anisotropy. Mohit, can you allow screen sharing for me, please?
Yeah. Sure.
Thank you. All right, we've talked about surface waves, but we haven't really talked about body waves. And so I want to look at body waves and different paths through the Earth and how they are designated. So on our top plot here, it shows an example seismogram, and the P, the little p, big P, the little s, big P, these are different paths of rays that travel through the Earth. And then when the wave is observed, they all get combined to form this messy but also quite wonderful seismogram. So as an example, if I have an earthquake here and a seismometer here, the little sp travels upward from the earthquake as an S wave, and then it bounces as a P wave. And the S waves are shown as dashed lines, and the P waves are shown as solid lines. So little p, big P travels upward from an earthquake as a P wave and then bounces. Sorry, this is a big, here we are. Here's the little p, big P. And little p, big P goes up as a P wave, bounces once, and then bounces again as a P wave. The SCS travels as an S wave to the core mantle boundary. When it bounces off the core, it gets a designation of little c, and then it bounces up as an S wave. So we have a convention that helps us name phases. So a ray that bounces off the surface gets a P or S added depending on what it is after the bounce. A ray that bounces off the inner core gets a little I added, and the outer core gets a little c added. A ray that travels through the outer core gets a capital K added, and for the inner core, a capital I or capital J added depending on whether it travels through the inner core as a P wave or S wave. And I would say that the J phase is actually quite rare because it's a very small amplitude phase. Sometimes when we want to refer to an interface for which there is not an official designation, we just use the depth. So P410S is a P wave that bounces off the 410 discontinuity, which we'll talk about later on in this lecture, and then turns into an S wave. So here are some examples. So in the figure to the left, S waves are shown as wiggly lines and P waves are shown as straight lines. So an SCS goes down as an S wave, bounces off the outer core, and is and goes through the upper mantle as an S wave. Here we see an S wave, it goes through the outer core as a P wave because the outer core being liquid, it cannot have shear waves. And then it's transmitted through the mantle as an S wave. So this is called an SKS. Here's an example of a P wave that travels through the outer core, travels through the inner core, travels through the outer core, and then back up through the mantle. So it starts out as a P wave, and it gets a K designation for traveling through the outer core, an I designation for traveling through the inner core, a K designation for traveling through the outer core, and then a P designation for traveling through the mantle as a P wave. We can see the same thing, except if it turns to an S wave at the inner core boundary, it's a PKJKP. And again, this is quite a small amplitude phase, so I've never looked for it, but I think you'd actually have to stack a lot of data to see it. Finally, I will say this is a P wave that travels through the outer core as a P wave, so it gets a K designation, and then travels through the mantle as a P wave, so it gets a Pkp designation. So once we've defined the paths of our rays, we can plot their travel time versus delta. And again, delta is the distance from the earthquake based on if this is a source and this is the receiver at this S here, delta is the angle through the earth that is subtended between the source and the receiver. So 180 degrees would be just opposite the source. And you can see the P waves here, which is the first arriving phase, big P, PK, IKP, and so on. And it's going to differ whether you have a shallow source or a deep source. Now, to make these plots, we have to know something about the velocity structure of the Earth. So we've developed radially averaged Earth models, JB in the 1940s, then PREM, ISB 91, and AK 135. AK 135 is the most recent and probably the most accurate model, but a lot of people still use the PREM model, which is still pretty accurate. And what we see is as I go from shallower depths to greater depths, the P wave velocity goes up. It drops at the core mantle boundary where it encounters the liquid outer core. Then it goes up again. And the S wave does something similar, except it drops to 0 at the outer core boundary because the outer core can't have a shear wave. So this will not necessarily give you the exact arrival time for a particular source receiver geometry. As shown by this plot here, the Earth has a lot of velocity variations within it. And these Earth models are radially averaged Earth models. So they don't take into account three-dimensional heterogeneities. So a great resource for calculating ray arrival times and ray paths is tau p, which can be found here. And Ed Gardnero has combined tau p with free mapping and plotting software called Generic Mapping Tools, or GMT, which we will learn about in one of our tutorials. So here's an example where he has plotted all sorts of rays, PCP, PK, little IKP, PKI, and so on. And so he has combined tau p, shell scripts, and GMT to make these plots. So then with appropriate arrival time information, we can make sense of the wiggles on a seismogram. So we can know where the S wave comes in and the little s, big S, for instance. So that is quite useful. Now, one thing that's worth noting is when ray paths form a caustic surface, so that means they turn along a plane here, they will undergo a pi/2 phase change. And that's because ray 1 here and ray 2 below it suddenly switch, and ray 2 becomes above ray 1, and ray 1 is below ray 2. So that causes a pi/2 phase change. A surface reflected phase will also get a pi phase change. And then If I have a P arrival, I have also a caustic surface, so I have a pi/2 phase change. So the total phase change due to a PP arrival is 3 pi/2. Now I want to talk about factors that affect amplitude. So the size of the earthquake determines the amount of energy released at the earthquake. And we'll talk about this more when we get to earthquake seismology. The distance from an earthquake. So energy falls roughly as 1/distance in the far field. The focal mechanism and your orientation to it. So the fault geometry and slip. This affects the radiation patterns. And again, we will get into this quite soon. And then which component of motion. So seismic instruments typically measure Z, which is the vertical channel, a north channel, and an east channel. And I will talk to you shortly about a transformation to Z, radial, and transverse. So different particle motions vibrate differently. So P motion is in the direction of the ray path. S motion is perpendicular to the ray path. And SH or SV may be dominant within your S wave. Finally, the type of seismic instrument also plays a role. Is it broadband and frequency sensitivity, or is it just a short period seismometer? And this is important because if my seismometer is only sensitive to higher frequency waves, such as 1 Hertz and above, it might not get a 10-second S wave. Or if it does, it'll be significantly reduced in amplitude. So the instrument affects the seismogram that you are observing. All right, now I want to talk about the geometry. So if I have a source at this star here, and then it is observed at triangle 1 or triangle 2, the azimuth is the clockwise path from the earthquake to the seismogram. And the back azimuth is the direction from the seismogram or seismometer back to the earthquake. Now, azimuth plus 180 degrees is not necessarily the back azimuth because of spherical geometry. So for instance, at station 2, the azimuth is about 10 degrees, and the back azimuth is about 260 degrees. So that's worth keeping in mind. And you can get programs that will calculate the back azimuth if you give it a latitude and longitude of the receiver and the source. If we zoom in on station 2, we'll find energy recorded on the northeast and vertical channels, the Z channel. And it's also useful to look at the radial and tangential or transverse channels. So the radial channel is in the direction between the receiver and the earthquake. And the transverse or tangential channel is perpendicular to that. So we will typically vector decompose the north and east channels in terms of the radial and tangential components. And then we will analyze one or both of those. And this is particularly useful with S waves. So we do this because PSV waves are naturally polarized in the radial and vertical directions, and SH waves are polarized in the tangential direction. So a P wave is going to, this is a map view, it's going to go down into the earth and come back up, and it's going to have all the energy on the radial channel or the vertical channel. Whereas an S wave is going to have energy on the SV channel, which will be up and down, or the SH channel, which will be perpendicular to this path. Here I show a cross section. So here's the earthquake, here's the receiver. You can see the SV motion, and we can see with a nearly vertically incident ray hitting your seismometer, your SV motion will be dominantly in the radial direction. Your P wave will be dominantly in the vertical direction, and your SH will be in and out of the board or this frame, and they'll be dominantly in the transverse direction. The contrast and properties between the mantle and the outer core makes for some interesting ray properties. And as I said before, reflections off the outer core denoted by little c, so PCP, PCS. Since the outer core doesn't transmit shear waves, the SH part of the S does not convert to a P wave and is reflected completely. So SCS is a strong phase compared to PCS or PCP, because all your SH energy gets reflected as the outgoing S wave. And you can actually measure multiple bounces of SCS. And this turns out to be useful for looking at attenuation, because you can look at this waveform, and this waveform, and see if they've been smoothed at all through attenuative processes, which we will get to later today. All right, in contrast, much P wave energy is transmitted. So we will look at some transmitted P waves. So for distances of 0 to 98 degrees, we get P waves that refract through the mantle. And for larger deltas, rays that don't leave the mantle are PCP. So they bounce off the outer core boundary. So here are some examples of P waves. Rays with slightly smaller angles of incidence get refracted downward at the core. So they hit the outer core and they are refracted downwards. So these are Pkp phases. And initially, the largest angle of incidence rays are observed at 177 degrees from the source. And then what happens is the rays are observed closer and closer to the source. So this is retrograde motion. And then later on, we move from B to C and we get prograde motion. So on a distance travel time plot, we go from A to B to C as we increase the angle of incidence. Or sorry, decrease the angle of incidence, because a vertical ray has a 0 angle of incidence. Next, we get the PK little IKP. So this one starts out at C, and then it goes this way. And again, it's retrograde. So it starts out here, and then it goes backwards. And then for still smaller angles of incidence, we get transmitted waves. So we have PK capital IKP. And these are waves that are transmitted through the inner core. And this is found in D through F. So we have A, B, C, D, and F in terms of shallower and shallower angles of incidence. Finally, I'd like to note a wave that's diffracted around the outer core. This is called P diffracted. And this is first observed at 98 degrees, and it can be observed at 180 degrees from the source. And here it is on our travel time distance plot. All right, the next thing I want to talk about is the composition of the Earth. And this is actually something that I'm quite interested in. So this is plot which isn't reproduced too well, shows the volume fraction on the x-axis as a function of depth in the earth down to 1,000 kilometers depth. And so in the upper mantle, which goes to the bottom of the transition zone here, we start out with olivine as your dominant mineral. Then we have garnet, clinopyroxene, and orthopyroxene. At shallower depths, above about 80 kilometers depth, the garnet turns into spinel. And above 30 kilometers depth, the spinel turns into plagioclase. So shallow upper mantle will have spinel rather than garnet, or plagioclase rather than garnet. Then as we cross a transition zone, the olivine changes into wadsleyite, and wadsleyite is a polymorph of olivine. So that means it has the same composition, but a different atomic structure. It's like diamond and graphite, right? They're both carbon, but they have different atomic structures. Wadsleyite changes to ringwoodite, which is another polymorph. So olivine, wadsleyite, and ringwoodite are all polymorphs. So they all have the same composition, but they have different atomic structures. And then ringwoodite plus majoritic garnet will change to ferropericlase and magnesium silicate perovskite, and also a little bit of calcium perovskite. So the crust is 6 or 7 kilometers in the oceans. It's roughly 40 kilometers in the continents, although it varies from roughly 15 kilometers to 80 kilometers. The upper mantle goes from the crust to, I said 410 kilometers here. I think it actually goes to 660 kilometers. It's called the upper mantle. The mantle above 410 kilometers made out of peridotite, which is olivine, clinopyroxene, orthopyroxene, garnet, spinel, or plagioclase, depending on what pressure you're at. Some seismic features of the mantle are often a high velocity lid or seismic lithosphere to about 60 to 100 kilometers depth, a low velocity zone below this to about 200 kilometers depth, and then cratons, which are the old hearts of continents, can have high velocities to 200 or 300 kilometers depth. So here's an example. These are velocity plots. So the x-axis is velocity, the y-axis is depth, done at a variety of different locations. And what we see at some locations is a high velocity lid, and then a low velocity layer under the lid. This is often associated with the Asthenosphere, and this high velocity feature is often associated with the lithosphere. Although going from the definition of a lithosphere as a mechanically strong component to seismically high velocities is actually a very difficult thing to do. So we will often call the high velocity lid seismic lithosphere rather than lithosphere. Both 1 and 2, so high velocity lid and low velocity layer that's associated with the Asthenosphere, are well defined in the oceans and less so in the continents, where things can become more complex. Under cratons, so we see these high velocities that go down to at least 150 kilometers here at the shields. They can go down as much as 200 to 300 kilometers in depth. And this is often associated with tectosphere, which is highly melt depleted mantle that seems to protect the overlying crust from deformation and melting, which is why we have 4 billion year old hearts of continents. For instance, the Kapval Craton, or in South Africa. Next, I want to talk about the transition zone. It goes from 410 kilometers to 670 kilometers depth. And this has 2 to 3 discontinuities that have velocity jumps that produce wave conversions, so P to S conversions, as well as reflections. So we have olivine to wadsleyite at 410 kilometers depth, At 520 kilometers depth, wallsite to ringwoodite. And this is really typically only seen in areas where you have subduction and you have cold mantle going down. And then 660 or 670 kilometers depth, we see ringwoodite turning to perovskite and magnesiovustite. Now these phase changes are temperature dependent. So as the temperature changes, the depth at which these phases will switch will also change. And this is denoted by the Clapeyron slope, which is the dP, depressure, detemperature. So the 410 kilometer discontinuity has a dP dt of somewhere between 2.5 and 4 megapascals per Kelvin. So this means as I increase the temperature, the pressure goes up. So the top of the 410 will actually get depressed to say 420 kilometers depth if I have higher temperatures. The opposite thing means the 410 goes up when things get colder. The 660 kilometer discontinuity has a dP dt of -3 to -1 megapascal per Kelvin. So this means that the 660 goes down when things are colder. So if I have a cold section in the transition zone should get thicker. If I have a hot thing ascending through the transition zone, such as the mantle plume, the transition zone should get thinner. Variations in composition could also cause variations in thickness. All right, and then the lower mantle. So this goes from 670 kilometers depth to 2891 kilometers depth, where we intersect the core. It's composed mostly of perovskite, which is now called bridgemanite, and then magnesiovustite and ferropericlase. Perovskite is the dominant mineral in the earth. So if I ask you what mineral dominates in the earth by volume or by mass, it's perovskite or bridgemanite. Near 2,550 kilometers, there's been a 2 to 3% S-wave velocity increase. And it seems to be perovskite turning to post-perovskite. So this is another polymorph. I don't know if there's a mineralogical name for post-perovskite other than post-perovskite. But that is thought as the likely reason for D double prime. And this layer doesn't exist everywhere in the lowermost mantle. Finally, there's an ultra low velocity zone, which is sitting right at the core mantle boundary. And it seems to be associated with a -5% VP drop, a -15% VS drop. And it could be due to melting, but it could be due to a number of things. And this is an area that's still being explored. So we really don't know what it is. Finally, the core is roughly at 3,950 degrees Kelvin. The core mantle boundary has a thermal boundary layer that's 1,400 to 1,600 degrees. So what that means is the mantle above the core is about 1,400 or 1,600 degrees cooler than the core. The outer core is a liquid iron alloy and may have a light element like sulfur in it. And the inner core is iron and nickel, and that extends from 5,100 to 6,400 kilometers. The inner core shows a directional dependence to wave speeds, and that's called anisotropic, and we're going to talk about that later today. All right, so when the Stein and Weiss-Session book was written, D double prime was a mystery. However, people have been able to produce post-perovskite in mineral physics labs. So it's thought now that this is just a polymorph that happens under certain thermal characteristics of the lowermost mantle. And I just want to show you how D double prime is observed. So here's an S wave, here's an SCS wave, and then here's an SCD where D is a discontinuity. So this little blob here is thought to indicate a reflection off the D double prime layer. And here are synthetics where people have put in a velocity structure and then developed synthetic seismographs. So we want to repeat, perovskite is now called bridgmanite, and bridgmanite is the dominant mineral in the earth, just because it takes up so much of the volume of the earth. So post-perovskite and perovskite, this dashed line is the Clapeyron slope. And what we can see is if I have a hot geotherm, so given by this hot line here, the temperature of the mantle never crosses into the post-perovskite stability field. However, if I have a moderate or cold geotherm, I will cross into the post-perovskite stability field. So if I have a coldish mantle, I will get a D double prime discontinuity, whereas if I have a hottish mantle, I will not get a D double prime discontinuity. The ultra low velocity zone, this can be identified through waves like the SPDKS, which travels at the surface of the core for a little distance, and the SKPDS, which travels through the base of the mantle on the other leg. And you can compare the travel times between these phases and SKS and figure out that there are low velocities, for instance, here or here. So we won't go into this in any great detail, but the idea is that looking at the Earth in creative ways tells us interesting things about the Earth. So ray theory is only an approximation, and this shows a simulation of S waves. And you can see as I go from time equals 60 seconds to time equals 900 seconds, the wave field is actually kind of complicated. And we can identify a ray with each of these phases. But you can see that things are fairly complicated. So we originally designated different regions of the Earth as A, B, C, D, D prime, D double prime. Really, the only thing that's used now is D double prime. And that is associated with a velocity jump roughly at, right here, 27 to 2,900 kilometers depth. All right, any questions on that?
Dr. Schutt, a few questions.
Yeah.
Can you please go to figure number 3.5-7?
Was that in my PowerPoint lecture?
Yes.
Okay.
Yes. These figures that you have on the right, so
yeah.
The interpretation is that the earthquake happened on the left side of that half sphere, and then there was a P wave that traveled. Yeah, there was a P wave that traveled from there, and then it split. So, I mean, did it split at the next boundary, or why did it keep splitting along the way? From the beginning, you know, I could not. What's the interpretation for? I could not understand.
So the P wave which is right here, creates energy that travels along all these ray paths.
Okay.
And so seismometers at a given location will only observe, say, one of those ray paths,
Okay.
but the energy travels throughout the Earth following these sort of ray geometries.
Okay, so you are showing the, you are not showing any reflections, right? You are just showing the transmissions through.
Yes. Yes, so there are also reflections.
For example, the next boundary that we have, the ray just transmits through that boundary, but it does not reflect anything, right? So in these, all of these diagrams, I don't see any reflections.
Yeah, like, except here. This third from the top layer is reflections off the outer core.
Okay, okay, I see.
But yeah, there is no PCP, for instance, which is a reflection of the P wave off the outer core boundary.
Okay, okay, I see now. And how do you relate these pictures to the plot on the left?
So this is a travel time versus distance plot. And as I go to shallower and shallower angles of incidence, I initially start out getting rays that follow the ray path given by A. And then as I go to shallower angles of incidence, I go from A to B, and which is going from retrograde motion. And then I go from B to C, which is prograde motion. And then I go from C to D, where I go from here to here. So this is retrograde motion again. And then I go from D to F, which is prograde motion. And that's shown by this. If I had a ray parameter travel time plot, you would see the ray parameter switch its slope, and that would show us the areas where it's going from prograde to retrograde motion. But you can't really see it too well on this travel time distance plot.
Okay, okay, that's great. Can you please go to 3.5-14 figure number? Yeah, this one. Yeah. So what do these lines mean? I mean, we have a solid line, then we have a dashed line, then we have a smaller dashed line. So what are those lines?
Oh, so these are velocity plots for different regions in the Earth. So for instance, this small dashed line here, T7, is for young continents. GCA is at a mid-ocean ridge. K8 is at a shield, and so on. And so the idea is to summarize the variations in velocities in the upper mantle.
Okay.
So that's why I wanted to show you some areas have a high velocity seismic lithosphere, but other areas like this GCA, this ridge, do not really have a high velocity lithosphere.
I mean, what type of velocity? Is it P wave, S wave, or what type of wave is it?
Oh, it's a P waves. Sorry.
Oh, that's fine. Also, when we talk about the boundary between the crust and the mantle, is that the Moho discontinuity, or is it the same, or is it something different? And is it reflected on this plot?
It is. So it's right here. It's this jump from 5 kilometers a second to roughly 8 kilometers per second. And it's shallower at the oceans, where it's going to happen at 6 or 7 kilometers depth. And it's deeper at the continents, where it could be 40 or 50 kilometers in depth.
Okay, okay. Let's see. So that's the Moho is the boundary between the between the crust and the mantle, is it?
Yes, it is. Yep.
Okay. Okay, thank you so much.
Yeah, great questions.
Thank you.
Are there any other questions? All right, let's take 10 minutes and then we will come back and do the second lecture. All right, it's been 8 minutes. I guess I'll wait another minute. Okay, now I'd like to talk about attenuation and anelasticity. So we can look at processes that affect wave amplitude on its path between the seismometer and the receiver. So transmission and reflection at interfaces, so we've already covered this. Geometric spreading, as the wavefront propagates outward and covers a larger volume, for energy to be conserved, the amplitude must go down. Multipathing, so focusing and defocusing of waves, analogous to mirages and light. Scattering, and this is like multipathing, but this occurs when velocity heterogeneities occur on the order of the wavelength of the propagating wave. And you really can't mimic this with ray theory. And anelasticity, which is a energy reduction due to mineral physics effects. And this actually causes a phase shift between the stress and the strain, producing energy loss. So we'll go through these one by one and then focus in on anelasticity. All right, so first, consider a wavefront spreading out on a flat Earth. So time equals T1, the wavefront is covering radius 1, at time equals T2, is covering radius 2. At time equals T1, the area of the circle is 2 pi r. At R1, at time 2, the area is 2 pi r2. If no energy is lost, then the energy per unit area of the wavefront is E naught over 2 pi r. And so as r goes up, then the amplitude is going to go down. So the amplitude goes as the square root of the energy. So the amplitude will go as 1 over the square root of the distance you are from your earthquake. Now, surface waves follow a ring whose circumference varies as a sine delta, where delta is the distance between the source and perhaps a receiver. The energy per unit wavefront goes as 1 over r, where r is the distance here from this axis to the surface, and amplitude goes as the square root of the energy, and thus decreases as 1 over the square root of a sine delta. This is a minimum at delta equals 90 and maximum at delta equals 0 and 180. So you're going to have amplitude maximized at the source and at the antipode of the source. Now for body waves, the wavefront expands spherically with the surface area of 4 pi r squared. So energy per unit wavefront is going to be proportional to 1 over r squared, and then amplitude will then be proportional to 1 over r. So these sort of back of the envelope calculations tell us that body waves lose amplitude as 1 over r, and surface waves lose amplitude as 1 over the square root of a sine delta, which is proportional to 1 over the square root of r, which means that surface waves lose amplitude slower than body waves. And we can see this. So when I showed you that plot of Rayleigh waves that went around the Earth multiple times, we don't really see that with body waves. And that's because body waves lose amplitude a lot quicker than surface waves. Now, seismic waves can be focused and defocused by velocity variations. So imagine I have this high velocity feature and it varies in topography. It will focus and defocus seismic waves. Rays prefer high velocity regions, and we can bring that back to Fermat's principle that suggests that rays will take the shortest travel time path between the earthquake and the receiver. So that's not necessarily the straight line path, because if it goes through a high velocity region, it could arrive quicker than if it goes through the straight line path. Now, rays are idealizations of wavefronts propagating, and technically a ray is a wavefront of infinite frequency. So to extend ray theory to finite frequencies, we can look at all rays that come in with a half wave period of each other, as these will constructively reinforce. And this is called the Fresnel zone. And this was actually done for electromagnetic waves, but it's the same for seismic waves. So all these waves that travel in this sort of banana-shaped region will coalesce at the receiver. And so the velocity variations in this whole banana-shaped region will affect the arrival time of seismic waves. Here's an example of multipathing in a slab. So if I have subduction going on and we have this sort of synthetic subducting slab, we can see that the energy travels in ways different from the geometric ray. So this plot here shows that the left and right directions will travel, well, the ray will travel through multiple paths, and you will get a right ray and a left ray. And you will get a left diffracted ray and a right diffracted ray. And so these will all add up to form your seismograms. So a simple ray traced through the earth, it will not suffice. Scattering is sort of like multipathing, but it occurs when velocity heterogeneities are the order of the wavelength of the wave. So in this case, ray theory does not do too well. So if I have velocity variations that are small enough, so down here, then the waves basically just see a homogeneous body. But if I have velocity variations roughly on the order of one wavelength, then we get scattering. Scatterers can be imaged via a couple of methods. So we can back project Coda energy. So here's my seismogram. As I go through the seismogram, I could consider that the energy comes from a wider and wider elliptical region of scatterers. So where this arrow is right here, this shows that energy could be scattered from anywhere in here. And for this arrow here, this shows me that energy could be scattered for anywhere in here. So what you could do then is you can plot a bunch of seismograms and figure out where these elliptical regions overlap, and you can find scatterers that way. You can also use the decay of coda waves to understand the statistical scattering properties. So for instance, at Cathedral Caves, Missouri, which is sort of a cratonic station, we see a lot of intrinsic attenuation. So from the earthquake to the time when things are damped out is less than 5 minutes. Whereas if I look at a moonquake, the moon energy just goes on forever and ever. It doesn't go on forever, it does damp out, but it undergoes a lot less attenuation. So that brings me to intrinsic attenuation. So attenuation or anelasticity is a process where the elastic energy in the earth is converted to heat when the seismic waves produce irrecoverable deformation. So to look at this, let's first use a spring analogy. So for a perfect spring, the equation of motion is the mass times the second derivative of the displacement with time times the spring constant times the location of the spring, and that equals 0. And a general solution to this is our displacement equals a e to the I omega naught t plus b e to the I omega naught t, where omega naught is a natural frequency of the system, and that equals the square root of k over m. Now, if we add attenuation, so energy is being lost to heat, then we also have a term here where we have I omega naught over 2q_t. And that creates a situation where we have the sinusoidal wave here, e to the I omega t, and then this damping term here. Since the real part of u of t gives the actual displacement, we can use Euler's rule that says e to the I theta equals cosine theta plus I sine theta to calculate the real value of u of t, and we get this here. And again, this is a sinusoidal wave and then a damping term. So we have an exponential decay in time, and the value of that exponential decay is determined by q. It's determined by 1 over q. So q is called the quality factor, and a high q means high quality, means low exponential decay, or it takes a long time for exponential decay, whereas a low q means high attenuation, and it means things will exponentially decay much quicker. So here is our cosine wave, and here is our exponential decay. We can talk about the time it takes for the signal to decay to 1 over e of its initial amplitude, and that's going to be 2q over omega naught. Now one can apply q to both p and s wave velocities, and typically we find that q of p waves is about 2.25 that of q of s waves. So that means s waves are attenuated more than p waves. So this is useful in that the decrease in amplitude from attenuation helps us understand the effects of earthquakes in a region. I can't speak for India, but I do know in the United States, in the eastern US, energy will travel much more efficiently than in the western US, and that's due to attenuation. So a magnitude 5 earthquake could be felt all along the East Coast, whereas a magnitude 5 earthquake in the West Coast will be felt only over a short area, a small area. Also, that Q plays an important role in the relationship between seismic velocity and higher temperatures. If we have the envelope of oscillation, then since this envelope equals a naught e to the omega naught t over 2q, then the natural log of that equals natural log of a naught minus omega naught t over 2q. So q can be found from the slope of the natural log of the amplitude envelope as it changes with time. So here's some examples I showed you from the normal mode lecture. We could convert this to a natural log, calculate the slope, and that would tell us the q factors here. If you have successive peaks one period apart, so one is at t1 and the next one's at t1 plus t, which is the wave period, then the amplitude ratio is going to be e to the minus omega naught t1 over 2q minus omega naught t plus capital T over 2q. And since capital T, which is the wave period, is 2 pi over omega naught, then A1 over A2 equals e to the minus pi over q. And after n cycles, A at t sub n is going to be proportional to A naught e to the minus n pi over q. So each cycle, we are going to diminish it by pi over q, e to the pi over q. So this tells us how a wave, amplitude of a wave varies with time at a given location. Another thing to look at is how amplitude varies in space. Since travel time is just distance over velocity, here I'm using c for velocity. A of x equals a naught e to the omega naught x divided by 2cq. And for theoretical methods, the integrated effect of attenuation along the rate path is t star, which is the integral of the travel time over q of r. And so t star is actually something that can be measured at different seismograms. So if I go to different seismic stations, I can measure t star variations between them and then say something about the q structure below them. In frequency space, a of omega equals a naught of omega e to the minus omega t star over 2. So this allows us to get at variations in attenuation in the Earth. So for a given earthquake observed at multiple seismometers, the relative variations in t star can be gotten at by ratioing the natural log of the spectrum of the event at each seismometer. So the natural log of a of omega is going to be minus omega t star over 2 plus ln a naught over omega. If I take the ratio of amplitude 1 and amplitude 2, so this is at station 1 and this is at station 2. Since they have the same source, the a naught terms will drop out, and I have e to the omega t1 star over 2 over e to the negative omega t2 star over 2. And if I take the natural log of this, then I have omega times the t star difference, delta t star, which is the difference between t1 and t2, times 1/2, which is right here. And variations on this technique are regularly used in seismology. I think what we find is t star does not vary as predicted by theory. And so some areas t star does vary as predicted by theory. And particularly, we see thermal variations lead to t star variations. And in other places, we don't see that. So we developed our intuition using an undriven harmonic oscillator. And let's add a harmonic driving force, e to the I omega t, to see what we can learn. So the differential equation describing this is now this, with a general solution, u of t equals a of omega e to the I phi t e to the I omega t. Plugging this back into the differential equation, gives an amplitude response and a phase response. So if I drive my system at its natural frequency, I will get a peak in amplitude. And the size of that peak in amplitude will vary with the Q value. I will also get a phase shift. So as I go to lower frequencies, the phase of the spring will actually shift by as much as pi. So damped harmonic oscillators are important in earth science as the earth responding to normal modes, a building's response to an earthquake, or a seismometer's response to an earthquake. U of x can be gotten by doing an inverse Fourier transform because we had U of omega. And what we find is U of x looks like this here. And that produces a travel time, amplitude versus travel time curve that looks kind of like this. However, if t equals the distance over the velocity, we would not expect energy to come in before this time, because that means that energy is traveling quicker than the velocity. So in this case here, the center case here, the energy, the arrival is acausal. And so we need to add another constraint. So we will say that the energy is 0 for t is less than x over our velocity. And c infinity is the phase velocity for an infinite frequency wave. So once we do that, we get this formula here, that c of omega equals c naught 1 plus 1 over pi q ln omega over omega naught. And this means that we actually have dispersion. So our phase, our velocity varies as frequency. The maximum velocity is going to be given by c naught, and that will be the arrival time right at x over c infinity. And then more and more energy will come in later and later. So from this, for P and S waves, we can get alpha as a function of wave period is equal to alpha at a wave period of 1 times this formula here, and beta equals this formula here, where L here is 4/9, and alpha 1 and beta 1 are the velocities at a wave period of 1 second.
Excuse me, sir.
Yeah.
Can you explain previous slide one more time?
This one here?
Yes, sir.
Or this one?
This one only.
Okay. So if we just apply the formula for attenuation of a spring, we would have energy coming in at both sides of travel time equals distance over velocity. But if energy is coming in before the travel times equals distance over velocity, that means it is traveling at a higher velocity than is observed in the substance. And we would say that's incorrect. So what we want to do is apply a constraint that produces something like this, that says no energy is traveling before the distance over velocity. And so when we do that, we get this relationship here, which tells us that the velocity is going to vary with frequency. So the fastest velocity will be infinite frequency waves, and that will be c of infinity, and that will travel at the perfectly causal time. And then other energy will come in later and later and form this sort of offset peak. And so what that means is the velocity of p waves, so alpha and beta, are going to be dependent on something like the wave period. So the wave period is proportional to the frequency, or 1 over the frequency. So alpha of t is going to be alpha of 1, which is the velocity at t equals 1 second, times this parameter here. And beta of t is going to be beta of 1 times this parameter here. So what this means is if I put in 40 seconds for t, then the t equals 1 second wave, which is beta of 1, is going to come in 5 seconds sooner than the t equals 40 second wave, which is going to be beta 1 times this value here, which will actually reduce the velocity by ln t, so ln of 40 seconds over pi times 1 over q. So you also have to ascribe a q value to figure out the effect on the arrival times. So for this reason, inversions of long period normal modes produce much lower velocity structures than inversions of short period structure, because higher frequency waves or shorter period waves see higher velocities than longer period waves. Now, so far, we've effectively treated the Earth as a system with a spring whose spring constant varies. A better system, although it's still imperfect, it still doesn't perfectly mimic the Earth, is a viscoelastic system. So we have a mass, and that mass is connected to a platform by one spring on one side and a spring and a dashpot on the other side. The dashpot applies damping, and its viscosity is proportional to the velocity at which m vibrates. So the resistance of the dashpot is going to be eta, which is the viscosity times velocity. What we see when we do this and we drive m is we have perfect energy, no energy loss at lowest frequencies, and no energy loss at high frequencies, and maximized energy loss. So attenuation is 1 over q at a frequency of omega tau, where tau is a constant based on these spring constants and this viscosity. What that further means is that the velocity that waves propagate through this system is going to be highest at high frequency and lowest at low frequency. If a step function, so this is a step function, is applied to the standard linear solid, it includes an instant response from K1 and K2, and then the K2 response decays with time because the K2 response, also has this dashpot in series with it. So our stress equals K1 plus K2 e to the minus t over tau, where tau equals eta over K2. So to get a feel for the system, we're going to look at first omega equals 0. So these are infinitely long waves. And in this case, the velocity at which n is vibrating is very slow. So that means eta is actually applying 0 resistance, and this arm here is basically detached. So the effective spring constant of the system is just K1. And that produces very low energy loss because the energy loss is based on this dashpot. And it also produces a low velocity because we only have one spring involved. As omega goes to infinity, then this dashpot basically becomes fixed. It offers infinite resistance. And so we basically have K1 and K2 in parallel, and that produces an effective spring constant of K sub 1, K sub 2 over K1 plus K2. Again, we have very little energy loss, but here the velocity at which waves travel is going to be higher because we have a higher spring constant. Then finally, for the middle, we have something in between. So we talk about the unrelaxed velocity as the velocity that infinite frequency waves see, and the relaxed velocity is the velocity that very low frequency waves see. In between, the dashpot will absorb energy, and the formula for attenuation as a function of frequency is going to look like this here. And the velocity is going to look like this. The important thing is the velocity is going from the unrelaxed velocity to the relaxed velocity, and we were going to have energy loss. So this is different from our damped harmonic oscillator because here we are maximizing attenuation at our omega t value. So the relaxed velocity is the spring constant, square root of the spring constant over the density. The unrelaxed velocity is 1 plus K2 over 2K1 times the relaxed velocity. This is pretty close to what happens in the Earth, with the exception there seems to be a band of frequencies. So if I measure attenuation as a function of frequency, what we typically see is from seismic waves of 10 to the minus 5 to 100 hertz, we see a sort of flat area of low Q and then higher Q on either side. So this is 1 over Q. So as I go up, I'm going up in attenuation. So we see this attenuation band dominantly at the frequency of seismic waves. We don't fully understand the physics behind this, but we know it occurs. Now, more recently than the book, studies have come out that suggest sliding occurs along grain boundaries, so subcrystals within the mineral crystals, so like little misorientations in your olivine crystals in the peridotite. And that could be a source of internal friction within the rock. And these studies suggest that Q is weakly a function of frequency. So Q is going to be some function of omega to the alpha, where alpha equals something like 0.2. And then Corrado in 1993 produced a paper that suggests the 1 over the velocity times dv dt equals d log our unrelaxed velocity dt minus f of a times the attenuation divided by pi times h star over RT squared. and f of a equals pi alpha over 2 times cotangent pi alpha over 2, where alpha is the frequency dependence. H star is the activation enthalpy of the mantle, and R is the gas constant. This is all an approximation, but what it does is it says that velocity goes down from the infinite frequency case, and it's a function of Q. We can throw in some numbers, and what we find out is that for Q of 50, d log Vp, so the percentage change in P wave velocity per degree Kelvin is going to be 2.18 minus 2.18 times 10 to the 4th Kelvin. So this means if I go up 100 degrees in temperature, I'm going to reduce P wave velocity by 2.18%. I'm going to reduce S wave velocity by 2.32%. Now, if I have a higher Q, for 100-degree temperature change, I'm going to reduce P wave velocity by just 0.82%. So what this means is that Q, which is actually a function of temperature, affects the effect of temperature on velocities. So at high temperatures and low Q, then 100 degrees is going to cause a larger velocity variation than 100 degrees variation at a colder background temperature. So we can plot the work of Jackson and Fowle 2010, and this is P wave velocity. This is just in olivine. And what we see is for 0 to 700 degrees, we see a linear trend, which just is the fact that the bulk modulus and shear modulus have a temperature effect, and that reduces them. And then at about 700 degrees, we see this additional anelastic effect, which causes a further decrease in velocity. And 1300 degrees or so is roughly the solidus. So we see mainly a 1/10 of a kilometer per second velocity variation near the solidus due to anelasticity. Now Q in the crust varies regionally, and this is part of the depth range that surface waves are sensitive to. So, and I said this earlier, surface waves in the eastern part of the United States see higher Q than surface waves in the west. And what this means is an earthquake in the east will be felt over a much larger region than earthquakes in the west. We don't really understand the mechanism causing the variations in crustal Q. It's probably thermal, but it may be more complicated than that. Oops. And then in the deeper Earth, attenuation is greatest in the Asthenosphere, where some of the lowest velocities occur. So here's a plot of Q with depth. And what we see is between 80 and 220 kilometers depth, Q is minimized. So that means attenuation is maximized. And here's a plot of lateral variations in Q around Tonga. Q is actually very hard to measure. But in this area here, we see very low Q, and that may be due to fluids. So we have a plate subducting going down here, and it's very high Q, and it's releasing fluids which are coming up here at this back arc spreading center. All right, any questions?
Dr. Schutt, I have 2 questions.
Yes, please.
Yeah, so you said that there's a decrease in velocity with increase in temperature, and it may be due to slipping along the grain boundaries. Is that right?
Yes, so the rate of decrease of velocity for a given temperature change is increased at low Q or high temperatures.
Okay, it's because at high temperatures the rock becomes more fluid, so there's greater chances of slippage. That's why along the grain boundaries. Is that the correct interpretation?
I think so. I don't really understand the physics behind it, but I think that's correct.
Okay, okay. And one more question. So, in the oil and gas industry, we are mainly concerned about depths between, let's say, 1 kilometer to at max 5 kilometers depths, right? So, do you think that temperature change is affecting the velocities in this range, or is it just much below, like 200 kilometers or 100 kilometers below the surface? Is that the range, or it's going to affect the rock? I mean, the velocities even at 0 to 5 kilometers.
I don't think intrinsic attenuation is going to affect seismic velocities between 0 and 5 kilometers. What could affect seismic velocities or amplitudes is the crack distribution. So as you go from higher cracks to lower density of cracks, as you go to greater depth, you're going to have higher attenuation just to cracks.
Okay, okay. But you're talking about seismic, but that's a low frequency, right? But if we talk about the logging and those things, those are acoustic, so they have very high frequencies, like the well logs and those things like VPBS. So do you think, you said the higher the frequency, more is the effect, or lower the frequency, more is the effect of temperature?
The higher and lower frequencies don't really affect the effective temperature on velocity. I think for 0 to 5 kilometers, your acoustic waves and your seismic waves would see the same velocities. But at greater depths, your acoustic waves would see higher velocities just due to the acoustic waves are approaching the infinite velocity limit, which approaches the unrelaxed velocity, whereas your seismic waves are more down towards the relaxed velocity, which is lower.
Okay, okay. I'm asking because we need to calculate these rock properties like Young's modulus and Boson's ratio using the acoustic velocity. So I was just thinking, is it gonna introduce too much error because of temperature in 0 to 5 kilometers? So the answer is no, right? So it could be less than 1%.
Yes, that's correct.
Okay, thank you.
Any other questions? All right. I would say use this last half hour to work on your homework. And I will be available for any questions that you have.
Okay, sir.
How's it going, everyone? Any questions? right, I'm going to go. So I will see you all in the evening. Have a great day.